dear students of Rajendra Water College. I know you are enjoying physics class. In the last 3 classes I discussed inertia, then momentum, force, impulse, with the second law of motion. And today what I am going to discuss, I will show you a video clip and then I will go to the board to describe today's class. Okay, today is lecture 4 and today is 11 by 0 to 0. Okay, you see it's chapter 3. You already know the name of the chapter. The name of the chapter is force. Today's lecture is 4. So let us first see a video clip. In the last class I finished here. So today I am going to start from this part, and I think you will enjoy the class. These are the topic of the first class. Today I am going to discuss first Newton's laws of motion and what is in our topic. Let us see. Then we are going to discuss Newton's third law of motion. So first I will show you some examples of Newton's third law of motion, and then what is in the third law I will tell you.
There are a lot of things happening in the world. Mass of the object, the more force it will take to accelerate the object, and applying more force will make the object move faster. Newton's third law of motion says that for every action, there is an equal and opposite reaction. If you exert a force on an object, it exerts an equal force back on you. For example, a ball hitting the ground exerts force downward. The floor exerts an equal force upward. This is the principle that allows rockets to launch or jellyfish to swim. By exerting a force downward, an equal and opposite force pushes upward, and the object accelerates. We can also see the third law in action when birds fly, allowing them to move upwards. Another good example of this law is skating. The skater pushes birds against the ground with their foot. The ground pushes forward with equal force. Since the wheels of the skateboard reduce the friction between the person and the ground, they are able to move forward for some time before forces slow them down again. Although these 3 laws were written down more than 300 years ago, they are still important now for understanding the way things move and represent the foundation of classical mechanics.
Okay, let us start. Let's watch another video clip.
Till now, we've only learned the first and second laws of motion. Oh, you're riding a bicycle. Have you ever wondered why a bicycle moves forward? Well, it moves according to Newton. This is the action. The floor reacts by pushing on the ball with the same force, but in the opposite direction. Action, reaction. Together, the floor and the ball form what's called the action-reaction pair. So now how it applies to your bicycle. When you push the pedal, the parts of the tire which touch the ground push it backwards. The ground also pushes the tires forward with the same force. So the parts of tires and earth form a pair of action and reaction. So what happens to the earth when your tires are applying force to push it backwards? Nothing happens to it, since the earth is very big as compared to your bicycle. The force supplied by your tires does not move it backwards, but force applied by the earth pushes your bicycle forward. So now you understand Newton's third law. Yep, the tennis ball is the right example. The ball and the floor are creating a pair of action and reaction.
So, actually we are going to discuss today Newton's third law of motion. So, what is in the Newton's third law of motion that we get from the video clips? Every action there is an equal and opposite reaction force, and if we consider the applied force, or I mean action force is F1 and the reaction force is F2, then F1 equals to minus F2. I mean sum of the two forces, action and reaction force, is always be 0. And today we'll also discuss the application of Newton's third law of motion. Okay, my dear students, I can write Newton's third law of motion. Newton's third law of motion is action force F1 equals to reaction force F2, but they are in opposite direction. That's why I show you the vector sign. If I write it, they are in opposite direction. So F1 equals to minus F2. Reaction force, that's why I write negative sign. So if we take the sum of the two forces, so sum of the action and reaction force is always 0. This is Newton's third law of motion. Okay, and now I am going to apply Newton's third law of motion to establish some other phenomenon of physics. So you write application of Newton's third law of motion. Application of Newton's third law of motion. So let us see another video clip. So you see, it is written law of conservation of energy, law of conservation of momentum. So from Newton's third law of motion, I will try to explain you law of conservation of momentum. And I will also describe some examples of conservation of momentum. Okay, let us see some examples of conservation of momentum. So first we have to know what is the law of conservation of momentum. Here you find there are some balls, two balls, one is blue and another one is red. They are moving along same direction with velocity u1 and u2. So momentum of the first ball is m1 u1 and momentum of the red ball is m2 u2. Okay, so if the velocity of the first ball is more than the second ball, then after some time they will collide, and during collision the blue ball gives a force, action force F1 to the red ball, and at the same time red ball will give a reaction force F2 on the blue ball. Let the action reaction time be t, and after that time they will again move, and they will move with different velocities v1 and v2. Blue ball is moving with velocity v1 and red ball is moving with velocity v2. So what is the law of conservation of momentum? Pause. Okay, first you write what is the law of conservation of momentum. I think you draw the diagram, but first we see What is the law of conservation of momentum?
Law of conservation of momentum. When two or more bodies act upon one another, then in the absence of an external force, the total momentum of all bodies of system in a particular direction remains constant. This is known as law of conservation of momentum.
Okay, let us see again the law of conservation of momentum. When two or more bodies act upon one another, then in the absence of external force, I mean there is no other force except action-reaction forces, then the total momentum of the bodies in a particular direction will remain same. This is known as law of conservation of momentum. Okay?
Absence of an external force, the total momentum of all bodies of system in a particular direction remains constant. This is known as law of conservation of momentum. Let two bodies, 1 and 2, have masses m1 and m2. Let their velocities be u1 and u2 before collision and v1 and v2 after collision. Initial momentum of body of mass m1 equals m1 u1. Initial momentum of body of mass m2 equals m2 u2. Total momentum before collision equals m1 u1 plus m2 u2. Final momentum of body of mass m1 equals m1 v1. Final momentum of body of mass m2 equals m2 v2. Total momentum after collision equals m1 v1 plus m2 v2. Body 1 exerts a force of action F12 on body 2. Body 2 exerts a force of reaction F21 on body 1. Suppose the collision lasts for t seconds. F12 equals rate of change of momentum of body 2 equals m2 multiplied by v2 minus u2 by t. F21 equals rate of change of momentum of body 1 equal to m1 multiplied by v1 minus u1 by t. Since reaction equals minus action, Newton's third law of motion, F21 equals minus F12. m1 multiplied by v1 minus u1 by t equals minus m2 multiplied by v2 minus u2 by t. m1 v1 minus m1 u1 equals minus m2 v2 plus m2 u2. According to law of conservation of momentum, m1 v1 plus m2 v2 equals m1 u1 plus m2 u2. Momentum of a system after collision equals momentum of a system before collision. Example, fired bullet acquires a momentum equals momentum of a system before collision. Example, gun and bullet. Initial momentum of bullet and cannon is 0. When the cannon is fired, bullet acquires a momentum mv. Cannon moves in the backward direction with a momentum equal to that of the bullet. To obey the law of conservation of momentum, final momentum of bullet and cannon should be 0. That is, final momentum of bullet and cannon equals mv plus mv dash equals 0. mv dash equals negative mv. v dash equals negative mv by capital M, where small m is the mass of bullet, capital M is the mass of cannon, v dash is the velocity of cannon, and v is the velocity of the bullet.
The example of conservation of momentum also in the universe.
Conservation of momentum tells us that the total momentum in any closed system will remain the same all the time. And since momentum is equal to mass times velocity, even if you have multiple objects going at different speeds that might collide, for example, the total momentum of the system before and after the collision will remain constant. So for example, these two balls, which in this case happen to be of equal mass, whether one of them is moving and causes the other to move, or they're both moving and collide and move off in different directions, the total speed and the total mass of the entire system always remains the same. So for example, if this had a velocity of 0, and that had the velocity of 1, the first one might impart some of its momentum onto the second, but the total between the two remains the same. And that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other. It even works, in this case I put Velcro, it even works if these two stick together, the total momentum remains the same. So for example, if I can get these two to stick together while one is stationary and the other is moving towards it, once they stick together, the total momentum will remain the same, so the combined objects will have half the velocity of the one initially that was moving. Conservation of momentum makes it actually quite interesting and challenging to move around the ISS if you don't have something to reach onto a handhold. Because if you get trapped out in the middle, there's no wiggling you can do, no swimming you can do that will get you over to a handhold so that you can pull yourself to move through the station. Because no matter what I do here, if I just stay floating in the middle, I'm just going to remain here in the middle since the total momentum of the system has to remain constant.
Let's see another example of conservation of momentum is,
After having studied the law of conservation of momentum, let's talk about its applications. When a gun is loaded with the bullet is fired. The bullet moves with a very high velocity. By Newton's third law, to every action there is equal and opposite reaction. Thus, gun recoils in the opposite direction. Since gun is much more massive than the bullet, it recoils back with very less velocity. Here, the mass of the gun is denoted by capital M, and mass of bullet is denoted by small m. As the gun is fired, the bullet moves forward with velocity of small v. As a result, the gun recoils back with velocity capital V. Now, according to the law of conservation of momentum, the total momentum before firing is equal to the total momentum after firing. That is, the initial momentum is equal to final momentum. Now, the initial momentum of the system is 0 because initially the gun and the bullet both were in a position of rest. Talking about the final momentum of the system after firing, so we can say it is equal to the momentum of bullet plus the momentum of the gun, that is small mv plus capital MV. Now if we rearrange the equation, we'll get the recoil velocity of the gun as minus mv upon capital M. Here the negative sign shows that the direction of recoil of gun is opposite to the direction of velocity of the bullet, so we can say the recoil velocity of bullet is opposite to the direction of motion of the bullet. The rocket works on the principle of law of conservation of momentum. The gases ejected from the nozzle gives a force upwards to the rocket. We can also apply law of conservation of momentum in case of rocket repulsion. If we ignore external forces, the momentum gained by the rocket in the forward direction is equal in magnitude the momentum of gases in the opposite direction. Thus the rocket and the exhaust gases push one another, and Newton's third law of motion is applicable in this case. Suppose the gases are ejected at a velocity of small v, and masses of fuel gases is denoted by small m. The mass of rocket is denoted by capital M, and it moves forward with the velocity of capital V. Now, according to the law of conservation of momentum, we know the initial momentum is equal to final momentum. Now, initial momentum of rocket can be stated as mass into velocity. Initially the rocket was at rest, so its velocity was 0. So we can write the initial momentum of rocket is m into 0. That is 0. If we talk about the initial momentum of the fuel, initially the fuel was also at rest position. So we can say the mass into velocity of fuel that is again 0, so initially momentum of fuel can be given as m into 0 that is again 0. If we talk about the initial momentum that is total initial momentum, we can say it as sum of initial momentum of rocket plus initial momentum of fuel, that both are 0, so the total initial momentum is also 0. Now, final momentum of rocket when the velocity v is being acquired by the rocket. So we can say if we talk about the final momentum of rocket, we can say it as mass into final velocity of rocket that is m into capital V. If we talk about final momentum of fuel, the mass of fuel is small m and velocity is small v. So final momentum of fuel can be given as mv. The total final momentum of the system, now it's given by sum of final momentum of rocket and final momentum of fuel, so we can say the total final momentum is equal to mv plus small mv, which gives us the total final momentum of the system. Now, if we equate, or if we substitute the values of total initial momentum and final momentum in this expression, we can say the initial momentum is equal to the total final momentum. If we rewrite the equation by more simplifying it, we can write the velocity of rocket that we denoted by capital V is equal to minus of small mv upon capital M. Here this negative sign denotes that the direction of velocity of rocket is opposite to the direction of motion of gas. So this is same the expression that we have already derived in case of motion of gun, or say required velocity of gun.
Okay, my dear students, now I come to the point that I was discussing. Between these two, I told you the examples, I described the examples, I told you some, I show you some clips of video clips of examples. Now I am going to back to my lecture. We are going to deduce the law of conservation of momentum. Okay, and I also describe it on the board. First you draw the diagram, two balls, B for blue, red, R, and they have mass m1, m2, initial velocity u1, u2. After action reaction force, their velocity becomes v1 and v2. Now how do we can prove the law of conservation of momentum? I'll show you. Okay, my dear students, I draw the same diagram here. You see blue ball, red ball, and the velocity of the blue ball u1 is greater than u2. u1 is greater than u2. So after some time they are colliding. Let the time of collision be t, and during the collision, blue ball gives a force F1 to the red ball, and the red ball gives the reaction force F2 on the blue ball. And after action reaction force, their velocity change, because you know Newton's second law, when there is any force acting on a body, then its velocity will change. So the new velocity, let the new velocity be v1 of the blue ball and v2 for the red ball. Okay, so let us go for calculation. Okay, my dear students, I am going to show you the calculation. Here I say u1 is greater than u2, and before collision you see the total momentum of the bodies. Pi is the total momentum of the bodies, m1 u1 plus m2 u2, and after collision the total momentum of the bodies, m1 v1 plus m2 v2. So we want to prove that p1 equals to p2. We are going to prove p1 equals to p2 so that it will support us the law of conservation of momentum. Okay, law of conservation of momentum. Okay, I will prove this law from Newton's third law of motion. From Newton's third law of motion, we know F1 equals to minus F2. F1 equals to minus F2. Here you see F1 and F2 are opposite and they are equal. So F1 equals to minus F2. So for F1, I write M1 A1. You know, from Newton's second law of motion, we know force is equal to the product of mass and acceleration. Similarly, M2 A2 is for F2. So if I put the values of the A1 and A2, I get M1 V1 minus V1 by T equals to M2 into V2 minus U2 by T. Cancelling T from both sides, finally we get m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. So m1 u1 we know initial momentum pi and pf is the final momentum m1 v1 plus m2 v2. That's why it proves the law of conservation of momentum. Okay, my dear students, I am going to conclude our lessons today. I am going to conclude our lesson. So I want to show you the conclusion by an example. I describe what is momentum and the law of conservation of momentum. You see there are 5 balls.